Good morning, just year 11s. Hey guys, good to see you all. Okay, so guys, I'm going to get straight on with this. I know I set you guys a homework, but I'm going to box off equilibrium first. We've got one more lesson to go. And then, which is industrial equilibrium and compromise. So we're going to box off equilibrium, and then what I'm going to do is I'm going to go to the specification just to show you that we've hit all the spec points. And then we can then start having a look at some exam style questions in preparation for your test. Cool, I like it. Let's share screen. Share. I want that one. Let's get rid of my face. Get rid of my face. Let's go stop cam. Not that it makes any difference. Right. So this is now. Yeah, there you go. Cool, it's all up and running. What I'm going to do is I'm going to pop out the chat and then close that. Okay. Get in there. Sorry, stuff this up, guys. There you go. You guys should be able to hear me now. I'm not going to bother closing anything. I'm just going to minimize that. Right. Can you hear me now, guys? Okay. What a mess that was. Let's start again. Can you hear me now? Yay. Okay. Right. Let's start again. So, 4 learning objectives today. Number 1, know your 3 processes: Haber, contact, direct hydration. Understand yield, rate, compromise. Number 3, know compromise reasons. Number 4, be able to use equilibrium flow diagrams. So those are our objectives for today. So I'm going to start off, I'm going to run through each process on its own. So the Haber process is the first one, developed by Fritz Haber. I'd love to know the year. It's give or take. It's around about 1917, I believe. Somewhere around then. I'm going to have to Google that now. Haber process invention. Year 1909. Look at that. Wowzer. 1909. Long time ago. And like I said, it was developed by a guy called Fritz Haber. Nasty little fellow. Not a nice guy. Also developed chemical warfare. And he got the Nobel Prize for this process. And in the ceremony where he was presented with it, Einstein refused to attend because of his other chemistry that he had contributed towards, as I said, chemical warfare. Anyway, so Haber process. So this process makes ammonia. Yeah, now just to tell you that ammonia is a gas, but we'll come back to that later. Yeah, but to make an ammonia, second bullet point, I need to now do a spin-off of this. Yeah, ammonia is used to, notice my capitalization, to make fertilizer. Yeah, you've got to be careful here. Fertilizer. You've got to be careful because you cannot say it's used for fertilizer because ammonia has a pH of 11, and if you pour it's a gas, so you couldn't exactly add it to the soil anyway. It'll just evaporate off the surface, and if you put it on as a liquid, it'll just boil away. So we use it to make fertilizer. That's important, and this is of course how we feed 7.8 billion people on our planet. So the Haber process is a very straightforward process. They take nitrogen gas from the atmosphere. The resource is from the atmosphere. And they take hydrogen gas. Now, hydrogen gas comes from the electrolysis of brine. Electrolysis of brine produces hydrogen. They take these 2 gases and they mix them together. Yeah, they input them like this into a reaction vessel. And inside that reaction vessel, it's a terrible line, don't like that. And the reaction vessel is sealed, closed system. What now happens is in here, we now have this reaction going on, N2 plus H2 in equilibrium to ammonia. Let's balance it. Let's try and balance it so it doesn't look a mess. 3 of those and 2 of those. We have inside this vessel, yeah, that reaction is taking place. Now, at this point, what we realize is that you then get an output. Now, just before I go any further, there is also inside this chamber is a series of metal, it's like a metal wire frame inside it. If I could actually do it like this, I really wish, if I do it like a highlighter, if I do a really skinny highlighter, it means you can see through it. Inside these, I should actually do it in gray. Color code it, Mr. Duncan. Come on. There we go. Should do it in gray. Now, there's a reason why it should be done in gray. Yeah, let's find gray. There we go. Skinny as I can. Inside here is a wire frame covered, and we can add this. Yeah, inside here, this here is a wire frame. I'm going to shrink my pen. A wire mesh covered in powdered covered in powdered iron metal, iron solid. Now, the reason for this is because iron is the catalyst for this process. It's the catalyst. So now sometimes now the wire mesh is genuinely true in this particular scenario. And the wire is also made out of iron, just so you know. They sometimes, instead of using a wire mesh, they sometimes use what's called a ceramic gauze, just to show you what that looks like. I'll show you ceramic gauze. Ceramic gauze. Now, the ceramic gauze, ceramics are unreactive. Yeah, look at that. A gauze, like the kind of thing that you use in your practicals. Yeah, this sits on top of your tripod. Now, that's actually not there's the material. No, I changed my mind. Maybe it's not. Oh, there it is. So this wire, this ceramic is then covered in iron powder. I wonder if I can actually find an example of a Haber catalyst. Haber process catalyst. I wonder if I can find a picture. Oh, the problem is they're not going to show one, are they? It's really frustrating. Not going to show you a real one in industry. I wish they did. It'd be so cool to see one, because it looks like a plate with like tiny holes in it, and then it's covered in a fine, shiny silver metal, which is iron. So the iron metal is the catalyst. Now, what now happens? Of course, the reaction vessel now gets split off into two areas. So what now happens is it then comes out. This is where I could probably actually make my vessel a bit. They have a valve in here. Yeah, this is a valve. Now, what then happens is once the equilibrium is established, they then release the mixture of the two gases. And this now enters a second chamber. Now, this chamber is a cooling chamber. Yeah, this here is called a cooling chamber. Sometimes called a condenser. It can be called a condenser. And of course, the reason being is because when the gases flow in, we actually have a mixture of unreacted nitrogen, unreacted hydrogen, and ammonia. These are all three gases. Now, what they do is they cool this down to about -70, I believe. It's about -70. And what that does is the ammonia cooling chamber condenses NH3 gas into liquid, into NH3 liquid. And that then forms at the bottom. So we have liquid down here. We have liquid ammonia, NH3L. Now they have another output there, which then is piped out. This is where I need to try and edit my diagrams to make them look really cool. Oh, darn it. Oh, there you go. So the liquid ammonia can then be taken out of here, NH3 liquid, and it is then bottled and sold. Yeah, bottled and sold. It's nice to put a nota bene on at this point, bottled and sold. So just to mention, you know, this is quite a nice thing to do. This is going to be in red, nota bene. Yeah. For transportation and storage, we always liquefy. The reason why we liquefy is because gases occupy much bigger spaces. Yeah, smaller, easier to store, easier to transport. You know, a container that holds this much liquid, to contain that as a gas, you're going to need it to be like this. So it's easier to liquefy it. Yeah, it's nice to note that as a nota bene. Now, here's the next clever bit. We're not quite finished with this because there's another output at the top up here. There's another output. I'm going to do this one in red since it was already there. Right, and then what we're doing is we are going to recycle unreacted gases. There we go. So this pipe here recycles unreacted gases. So the unreacted gases, which include hydrogen and nitrogen, these unreacted gases simply remain as a gas at this temperature. Yeah, and they go up the pipe and they are then recycled. Only nitrogen and hydrogen. All the ammonia goes down, it forms as a liquid and drops out and is bottled and stored. So this is recycling unreacted gases. Recycling unreacted gases. I like it. And this is a good thing, because what this means is, this is a common question at GCSE, and I'm going to add the question. Yeah. Question: how does a company producing ammonia achieve a 98% overall yield when the yield is only 35 per pass? It's passed through the reactor. It's a very easy question. You simply say it recycles unreacted gases. That is it. Yeah, the answer is they recycle. They recycle unreacted hydrogen, nitrogen, H2 and N2. They recycle unreacted H2 and N2 and reuse it. Not complicated, and it's weird, isn't it? Because there's an overall yield and then a yield per pass, which is really stupid. But that question does come off and often throws students off. Yeah. Okay. Next thing. So we kind of get like this kind of basic concept of what the Haber process is doing. Yeah, and it kind of makes sense. So now what we need to do is talk about the conditions needed for this. So inside this box, inside the vessel, what conditions do they use? So let's do Haber process conditions. So Haber process conditions, nice and easy. Number one, temperature. Temperature is 450 Celsius degrees C. Okay, now this temperature is a compromise. Let's explain why it's a compromise. The reason why it's a compromise is because if you get given the equation, what we realize is that the forward direction is exothermic. Now this immediately tells us exo, this is hot. Yeah, the forward direction is exothermic. Now what that means is, bullet point, lower temps favor higher yield. Yeah, let's just prove this with GCSE. So knowledge, forward reaction is exothermic. Oppose, we lower the temperature, therefore equilibrium raises temp. Favors, so favor exo reaction. So the equilibrium favor, it's trying to raise it, favor exo reaction. Yeah, shift left to right, because the forward direction is that one. It's going to favor the exo, it's going to go that way. So shift left, shift L to R, short version of GCSE. Yield increase increase. The short form of COFC, look at that. It looks like I'm quite literally writing in hieroglyphics. It's kind of cool, really, isn't it? I like it. So anyway, so we know that lower temperatures favors higher yield. I'm just going to move all of that. COFC is awesome. Love COFC. Oh dear, didn't want to move him. Go on. There we go. So we don't really need that. So we know that a lower temperature favors higher yield. But there's a problem. But that is one big but. Yeah? So, but lower temperatures, lower temps will lower the rate. Will lower the rate. Now, Mr. Duncan, for shift left to right, what if the position is already to the right, but it just shifts further? You'll still say it'll shift left to right. You'll still say the same thing libs. Remember, it is never possible to have 100%. So you can always shift it more, and you would comment on the shift being the same. Yeah, you could go from an 80% yield to a 90% yield. You could go from a 90% yield to a 92% yield. You're still shifting it from left to right. Yeah. So you're going to lower the rate. Now that's a problem. Now just to talk you through this in understanding wise, this is where I always try desperately to do this. So I think I might have done this already. I think I did. Yeah, so I'm going to make a mess of this. I always do. So A equilibrium B. Start at 10, got 0. At minute 1, I'm going to zoom out just a touch. Yeah, this is experiment 1, by the way. So after 10 minutes, I have 7 and 3. Okay. Right, and I've reached equilibrium. That was the time at which equilibrium it took. It took from 0 to 10 minutes, and I've now reached equilibrium. Reached equilibrium in 10 minutes, and I have made a yield of 3. Everyone here would agree that the yield is poor. That's a poor yield. Yeah, poor yield. 30%, it's garbage. Yeah, so what we're going to do is we're going to change the scenario. Yeah, we're going to repeat. Now what we're going to do is we're going to do experiment number 2, EXP number 2. And what I'm going to do is I'm going to lower the temperature. The forward reaction was exothermic. I'm going to shift the equilibrium from right to left, left to right by lowering the temperature. So let's by the way, let's give this one a temperature. Let's say that this one was conducted at 100, let's say 200 degrees Celsius. Right, we're going to do experiment number 2. And we're going to do exactly the same one. A equilibrium B. Still exothermic, we know that, but our temperature we're now going to choose is we're now going to go to 100 degrees Celsius. So we're just going to lower the temperature by half. Now we start off with the same thing, 10 and 0. And now what this means is it now, for me to get from start, I feel like if someone's messaging me, there's usually an issue, but I'm going to keep going anyway. So start. So for me to reach the new equilibrium shifts to be 5 at equilibrium, at equi, I have 5 and 5. I've increased my yield. Yield increased. My yield increased. However, it took 20 minutes to reach it. It took 20 minutes. Now that's a problem, because what we realize is there's a problem, because in 10 minutes time, I get a yield of 30%. At 100 degrees in 20 minutes, I get a 50% yield. Well, what we'd actually realize is that this lowering of the temperature, this was bad. The reason being is we're just going to say, let's not lower the temperature. Let's just run this one, run this twice. Because if we run that one twice, the time is the same. Yeah, the total time would be 20 minutes. 10 minutes, 20 minutes. If we run this twice, it will take 20 minutes. And I will create an overall yield of 60%. I may as well just keep the conditions the same and just run it twice. This is the whole point of a compromise. The lower temperature did give me a better yield. It did. We love this. But the problem is the yield increase that I got was not enough to compensate for the extra time I need to reach equilibrium. So this is why you have a compromise. Now, so lower temperatures favors high yield, but lower temps will lower the rate. So we have a compromise. We have 450 degrees Celsius. And what this does, and you can put this in red, a reasonable yield and a reasonable rate. And sometimes they ask you to explain why, and then you have to do that one. Yeah. You'd say, if I lower the temperature, I'll get a better yield, but the lower temperature means I'll have a slower rate, so overall, it's not as beneficial. Yeah? So it's nice to talk about the temperature compromise. Can I just point out, pretty much all industrial equilibriums have this. They all seem to suffer from a similar problem. So they all gain their own compromised temperature. Okay, my computer's decided to have a fit. Okay, so let's continue with the next Haber process condition. The next Haber process condition is the pressure. So we've got temperature. The pressure for the Haber pressure is 200 atmospheres. I'm actually going to write atmospheres. Atmospheres. I like it. Now this is insane. Now, if anybody here goes diving, they'll have a better understanding of what this is actually saying. So when you go diving, pressure is a bizarre thing. When you go diving, just going to draw it as a. When you go diving, when you're standing up here on shore, yeah. When you're standing up here on shore, yeah. You're waving hello, yeah. When you're standing on the shore, you are feeling the pressure of what is described as 1 atmosphere, 1 atm. This is all the air above your head pushing down on you. It's called 1 atmosphere. When you then go diving, yeah, when you come down to here, what you now realize, let's put a little tank on his back. That's a terrible diagram, absolutely terrible. There we go. So when you go diving, every time you descend, I want to say he's diving. It does look like a terrible diagram. I'm not entirely sure. That's just awful. Yeah, my bad. Anyway, when you go diving, every time you go down 10 meters in water, you increase the pressure by 1 atmosphere. So 10 meters down is this. So what that tells us is if you were to take the entire atmosphere, if you had the entire atmosphere above your head, yeah, so this is the atmosphere above your head, and then this here is space, yeah, all of this air, all of this gas pushing down on you is the equivalent of 10 meters of water. Yeah, it's kind of cool that. So anyway, you go down 10 meters, you're now at 2 atms. So, okay, so how deep do you need to go to get to 200 atmospheres? How deep do you need to go, folks? Somebody on the chat and give me an answer. Any ideas? How deep do you need to go to get to 2 atmospheres. Look at helping. Check it out. I like it. Well done, helping. Give or take 2,000 meters. This is the same depth as the Titanic, which is insane. So, can I just point out there's only about 8 or 9 submersibles around in the world that can get that deep without being crushed by the pressure. Yeah, that is insane amounts of pressure. And they use this in the Haber process. So what they do in the Haber is they build, do you want to see a vessel? Cool, man. Haber process vessel. Where are the vessels? Give me a real picture of a vessel. I want a new one. I want a new one. Give me a new one. Oh, chemical reactors. Yeah, it's probably something like that. So these vessels, there we go. So that's a pharmaceutical reactor, but it'll probably be very similar to the Haber one. So can you see how thick the metal is? Yeah, the metal's crazy thick. These things have to be incredibly tough because what they're doing is taking this vessel here. They're taking this vessel here and they are making it so thick that it can cope with these kinds of pressures. Yeah, these things are made from solid like titanium steel alloys and cost millions of dollars because the pressure in here is insane. So it's a bit bonkers, really. Now, this is a compromised pressure because what we know, so pressure compromise. Pressure compromise. If we look at the equation, N2 plus H2, equilibrium, ammonia, balance it, we realize that we have 4 moles on this side. I'm just going to show you where they come from. 4 moles on that side, and we have 2 moles on this side. What that means is 2 moles. We realize that in order to favor this, we want to push it that way and higher pressures. So the bullet point is high pressure favors high yield. High yield. Right. So turn up the pressure. But there's a problem, isn't there? Because if you take a vessel, and you increase the pressure inside it. Yeah, you take the vessel and you just add more and more gas. Yeah, so all we're going to do is this is going to be vol of gas versus pressure. And what we're going to see is we're going to see, it's actually going to be an interesting curve. Yeah, I think that's right. Is that right? Volume and pressure? Yeah. It would actually be volume of gas. It should be the volume of the container. It doesn't really matter. The volume of gas added, sure. And pressure. So what realize is that if you just keep going, eventually it's going to rupture and the whole thing would explode. So the compromise here, the compromise bullet point we need, compromise. High yield, it's the cost of the equipment. It's yield compromise. Yield versus cost of equipment. Because I'm not going to lie, we're an amazingly good engineering species, and we could make a vessel that could go to 1,000 atmospheres. We could make a vessel that could probably manage 1,000,000 atmospheres. Probably could. But the problem is the increased yield you're going to get just doesn't warrant the cost of the extra equipment. The equipment has to be replaced every 10 years as well, which is another important problem. So you don't have to pay for a crazy expensive vessel just to get an extra 2% yield. It's just not worth it. Just not worth it. So those are the conditions. So in summary, let's summarize. Haber process. Summary. Iron metal catalyst. Iron metal catalyst. 450 degrees Celsius, 200 atmospheres. Yeah, and both of these here are compromises. One in terms of compromise. One in terms of the temperature, the yield versus the rate, and the other is the yield versus the cost. Yeah, that sums up the Haber. Okay, so I'm just going to quickly go up to my learning objectives because I realize I haven't got a long lesson left. So we can tick off the Haber. Tick off Haber. And we can tick off yield rate compromise. We can tick that one off. We've also discussed the reasons behind them. However, I'm going to mention, yeah, we've covered that one as well. So I just want to quickly show you a flow diagram. So I've tried to actually draw exactly what I had here. That was a bit of luck, by the way. By the way, I can show you exactly, like this is the real, oh no, this is a different one. This is ethanol. Look at that. Look at that beast. It's amazing. I'll talk more about flow charts next lesson. So the next lesson, now that we understand these two, now that this one and this one is done, I'm just going to tick off contact and direct hydration, focus on exam question flow charts, and we'll be done. I did think that it might take a little bit longer. I do need to explain all these things, and it's taken a bit longer than I thought. Anyway, so I'm going to leave today's lesson there. I hope you found it useful, guys. We now know that Ammonia is going to do an amazing job of putting together a sheet of online resources that this is where I just need to stop sharing my screen. There we go. So she's going to, we've created an online sheet that people can now add to, where you can, if you find yourself watching a YouTube video or doing a worksheet or something, or using a resource online, yeah, you can say the topic that it was useful for, the concept that it reinforced, give the link and give its usefulness. I think this would be really handy for you guys to be able to have access to. Anyway, guys, I'm going to leave you be. Have a good rest of your day. I'll see you next lesson. So 2 more lessons left, folks, and then your test. So you still got another week here. See you soon, guys.